Section 2.5 is the last method for solving the first order ordinary differential equation, and it is for linear differential equation. This is a linear first order differential equation. We have defined linearity before. Linear means here y and y prime, they have to be to the power of 1 only, and they are not multiplied by a function of y. To solve linear first order differential equation, we have to rewrite it in a standard form. Standard form means the first coefficient has to be 1. This can be done if we divide by a1x. So this will become 1. This is going to be a different function. We call them px and qx. So this is a first order linear differential equation in a standard form. To solve it, simply we have to use this rule, which is given by the theorem. Yx, the solution is 1 over mu q. Q is this, and the mu is e to the power integration of p. P is coefficient of y. This rule can be derived, or this theorem can be proved. The proof is not required really, but it can be proved using integrating factor, which means if you solve this equation using integrating factor method, you find a mu x and a mu y and so on, you are going to end up with this rule, which means that every linear differential equation can be done using integrating factor, because this comes from integrating factor method. So every linear differential equation can be done using integrating factor. So if a linear differential equation was given to you as a question, if you could not see it's linear, you will end up solving it using integrating factor method, which is much longer method. Now let us see an example. Here, find a particular solution, because initial value is given. Never mind, this is a linear because you have y and y prime to the power of 1, and this is a function of x only. So it is already in a standard form. So px is equal 10x, and the qx is equal to cosine square x. Yx is equal 1 divided mu x qx dx. Mu x is equal to e to the power integration of p, which is equal to e to the power integration of p, which is 10. 10 is sine over cosine, so mu x, so it's easy to integrate, it's ln secant x. We don't need an absolute because we need one only mu x, we don't need two mu x. This is secant. So yx now is equal to 1 over mu q. So secant x, and the q is cosine square x dx. Now yx is equal to cosine x, and this is 1 over cosine times cosine square, so it's integration of cosine. So yx is cosine x sine x plus c. You can find c because initial value is given, so 2 is equal cosine 0 sine 0 plus c. Sine 0 is 0, this is 1, so c is equal to, and final answer is going to be yx is equal to cosine x times sine x plus 2, which is this. Orthogonal trajectories or perpendicular curves is a simple application for chapter 2. In order to talk about orthogonal trajectories, we need to remember two simple facts from calculus or from school. The first one, if we have two perpendicular lines, slope of this one is m1 and the slope of this one is m2, then m2 is equal to minus 1 divided m1. This is true not only for lines, for any two perpendicular curves. The second thing we need to remember that dy dx is the slope of the curve given by y. Let's consider the following example to see how to find orthogonal trajectories now. Find equation of orthogonal trajectories which are perpendicular curves, for the curves given by y equal x squared plus c. So we need to find the perpendicular curves to the given curves. 3 steps we will have to do to find. See, these are some of the given curves. Which are the given curves are what? Are y, which are parabolas. We need to find equation of perpendicular curves, which are family also of curves. 3 steps. The first step, find the slope of the given curve from the derivative. Second step, from the slope of the curves, you can decide about the slope of the orthogonal, which is perpendicular. So slope, which is y prime, is minus 1 over 2x. This is for the orthogonal. So this is differential equation of orthogonal trajectories. So what is third step? Solve the equation number 2 to find equation of orthogonal trajectories. Now you have 5 methods to solve this differential equation, which we have done in chapter 2. It can be separable, homogeneous, exact, or integrating factor, or linear. For example, this is separable. You can solve it and find y, which is equation of orthogonal trajectories. Here is another example for finding orthogonal trajectory. Given these curves, find orthogonal trajectories for these curves. Like we said before, we have to do 3 steps. The first step, find the slope of the given curves, which is the derivative of the given curves. You see, you cannot differentiate by saying simply 2cx because the derivative cannot have c in it. So you have to separate c and then differentiate. You can differentiate by saying square denominator, derivative of numerator, minus numerator, derivative of denominator equal to 0. 0 multiplied by this, so you are going to have x squared y prime minus 2xy is equal to 0, which is this. And then you can rearrange this to find dy dx for the given curve. This is step number 1. Differentiate provided c should be eliminated. Second step, find the slope of orthogonal simply by taking reciprocal of this and change the sign. So instead of 2y divided x, it is x divided 2y. Instead of a plus, it's minus. If it was this minus, this will be plus. Step number 3, so this is now differential equation of orthogonal trajectories. To find equation of orthogonal trajectories, solve it using any of the 5 methods. This is separable, so you can solve it as separable to find equation of orthogonal trajectories, which are given here. These are the given curves, which are cx squared. These are the orthogonal curves, which are the ellipses, family of ellipses. Now, a very quick conclusion about the chapter. See, in this chapter, we did 5 methods for solving first order differential equation. It is very important in which order we think about the methods. We should think in the following order. If a differential equation was given to us, we should check linearity first. Is it linear or not? Because linear can be checked by looking and it is easy to solve. If it's not linear, we have to check if it is separable, because separable also is easy to solve. And if not, we have to check if it's homogeneous. If not, we have to check exactness, and it has to be written in a certain way. And if not, we have to see integrating factor, which is the longest method. It is very important that we think in this order to avoid any confusion. And we also said that every linear can be done using integrating factor. So if we don't see it's linear, and if we don't think about linearity first, we might solve it using integrating factor, which is going to take much longer time. So it's very important that we think in this order.